Okay, can everybody see my screen here? Let's do what we did on Monday, and let's start by looking at this project that we're going to be working through together again. A lot of you, as far as responding to the question, waited until the last minute here. I would encourage you to try to do it earlier so that you can have time to ask me questions if you need to. A few people did ask me questions, and that was good. So again, we have this pipeline that we're trying to lie down through a wetland to get from well A to well B. And the initial modeling process that we talked about is to model this wetlands, even though it's not a rectangle, to keep things simple, model it as a rectangle. See how well that model does, see if it seems reasonable, and then ask whether we can improve the model or not. So this was the drawing that I made on Monday, modeling the wetlands as a rectangle. And the real issue was, how big should X be to minimize cost? Where X is this vertical distance in the north-south direction from B up to the spot where the pipeline would go into the wetlands. Okay. Again, it's not a rectangle, but pretending it's a rectangle, you'd be going up straight up from B somewhere and then cutting across the wetlands, pretending there's wetlands over here, even though there's not. To keep things simple. That's again a modeling kind of thing to do, is to keep things simple at first. That's an unknown. X is the variable that you're interested in. You need to figure out how this length right here in this right triangle depends on X. What do we use to get that? What theorem did we use to get that? Trying to hide it here. Pythagorean theorem. The length of this side was 350 feet. This is a right triangle. The length of this side was 830 minus X. It depends on X. This side is the hypotenuse of that triangle. So its length squared equals the sum of the squares of the lengths of these two sides. And therefore, the length of the hypotenuse itself is the square root of the sum of the squares of the lengths of those two sides. Careful though, this does not simplify to 350 plus 830 minus X. When you take the square root of the sum of two squares, you cannot just get rid of the square root like that. So we have to work with this function as it is. But this is a distance, it's not a cost. We are after the total cost as a function of X. It's not a cost yet. And that's what I was wanting you to do for the completion credit for today. And by the way, a reminder with this completion credit, it's not just toward the homework and completion part of your grade, it's also part of the project 2 grade. So you do want to make sure you take it seriously and make sure you're getting it in, giving yourself a little bit more cushion time. So what is this cost now? We have to look at the data that we're given again. Those lengths are in feet. If we can multiply by costs that are given in dollars per foot, that will give us a cost in dollars, right? Because the units of feet will cancel. The pipe itself is given as a cost in dollars per foot. And over normal terrain, it's given as a cost in dollars per foot as far as installation goes. And over normal terrain, the distance you go is X. So just add those costs, $1.50 plus $1.20. The units for that would be in dollars per foot times X, because X is in feet. And don't worry that one of those is plural and one is singular, they still do cancel. And this product has units of dollars. And it does simplify to 2.7 times X. That's what I was wanting for the first question that I sent you, is that constant is 2.7. So the formula for the cost of installing the pipe along this part right there is 2.7 times X. What about the part that goes through the wetlands? Well, its length again is this thing right here. I've got to multiply that by the cost in dollars per foot for installing across the wetlands. My assumption is that these two costs are still in play. Now, you might have thought maybe this one's not, since it emphasizes normal terrain. And if you did that, I counted what you did is okay. But my assumption is that's both included in the wetlands because of the word additional right there. In addition to those other two costs, the cost for the pipe and the cost per foot of installation, there's an additional cost to sort of dig this extra trench or something at $60 per hour. But that's a cost in dollars per hour. How do I convert that to dollars per foot? I need to convert it to dollars per foot if I'm going to multiply by the length of that line in feet to give me units of dollars. How do I convert that to dollars per foot? What am I not using? You want to go ahead and say? This is in $60 per hour. Do you see what I'm showing there? How do I convert that to dollars per foot? Exactly. It's 300. It can dig 300 feet of trench in 10 hours. In other words, that's the same as 30 feet per hour. And if you think about taking these two things and putting this information together, taking $60 per hour as a cost rate per unit time and dividing by 30 feet per hour as a rate at which you can dig the trench, the hours cancel and you are left with $2 per foot. You can try particular hours if you want to double check that that works. That's what you would want to also add to 2.7 here to get the cost in dollars per foot for crossing the wetlands. 2.7 plus 2 is 4.7. That would be in dollars per foot. Think of it as 2.7 plus 2. That gets multiplied by the distance across the wetlands. Square root of 350 squared plus 830 minus x quantity squared. I think it actually turns out best here to not try to simplify this thing under the square root. When we're about to take the derivative to try to minimize this cost. I haven't tried this in a while, but I think it works out best to keep it like that and not try to simplify it. That's our cost as a function of x. Again, this is dollars per foot, this is in feet. So those cancel. This whole product has units of dollars. That's our cost, the sum of these two things. Now try to minimize. Take the derivative. And after I take the derivative, what do I do? Sorry for those who are in the waiting room. After I take the derivative, what do I do? Set it equal to 0, solve for x, solve for the critical points. So the derivative of that part is easy, right? Just 2.7. What derivative fact am I going to need to differentiate this part? Besides the power rule. Chain rule for sure. I think we can avoid the product rule. Think of the square root as a 1/2 power. Think of this entire thing right here as 350 squared plus 830 minus x quantity squared, all to the 1/2 power. So the outside function is the square root function raising to the 1/2 power, and the inside function is this thing. So that's a chain rule problem. Keep the 4.7 there as a constant coefficient. 4.7, bring down the 1/2, so I get times 1/2. 350 squared plus 830 minus x quantity squared to the negative 1/2, then multiply times the derivative of the inside function, And again, you don't have to expand this out. The derivative of that is 0. The derivative of this you can think of with the chain rule again. Bring the 2 down in front. You subtract 1 from the exponent, it's a first power. Now multiply times the derivative of 800 minus x, negative 1. Looks pretty complicated. Yeah, it's pretty complicated. Looks like it might be difficult to solve for where this equals 0. But I'm pretty sure it's doable. If I set this all equal to 0 and solve for x, I think it's best to think of it as put this part over on the other side as a fraction and think in terms of cross multiplication. Somebody has a question? Thank you. Right there? Is that the mistake you were talking about? Yep, okay, thanks. That's an 830. I think it'll be helpful to put this entire thing on the other side and effectively cross multiply. So when I do so, well, the 2's do cancel here and here. The negative 1 on the left side of this equation with the 0 on the right, when I add to both sides, I'll get a positive 1 on the other side, so the negative sign goes away. Looks like I'll have 4.7 times 830 minus x over the square root of 350 squared plus 830 minus x quantity squared. I could square both sides right now, but I can also first just multiply both sides by that square root. And if you want to think of 2.7 as 2.7 over 1, then you can think of it in terms of cross multiplication. But you can just think of it in terms of multiplying both sides by the square root to cancel on the right side. Now square both sides. Everything look okay? Make sure you're looking for mistakes here. 2.7 squared, 7.29. So I'm squaring both sides. The square root goes away. .7 squared is 22.09. And I get an 830 minus x quantity squared. And yeah, this is part of the reason it's good to just leave it like that and not expand it out, because now I have an 830 minus x quantity squared on both sides. I don't have to try to expand it out and use the quadratic formula. I could. I can just try to isolate 830 minus x quantity squared on one side and then take a square root. Coefficient of 830 minus x quantity squared there is the 7.29. Coefficient here is 22.09. If I subtract 7.29 times 830 minus x quantity squared from both sides, it'll cancel on the left, and 22.09 minus 7.29 is 14.8. I'll get a 14.8 times 830 minus x quantity squared on this side, and on the left side I'll have the 7.29 times 350 squared. Divide both sides by 14.8. 7.29 divided by 14.8. Not a very nice number. I'll go ahead and write it down anyway. 0.53378378838 times 350 squared is 830 minus x quantity squared. Now take the square root of both sides, allowing plus or minus sign on the left side. Let me just go ahead and multiply this out now. Multiply that times 350 squared. Plus or minus that before the square root. But now take the square root of that, raise it to the 1/2 power. Looks like it's plus or minus 255.712, say, equals 830 minus x. So add x to both sides and then instead of a plus minus on this side, do a minus plus, so to speak, on the, by subtracting 255.712 when it's a plus sign and adding it when it's a minus sign. It's like x is 830, and for fun, I can just go ahead and write minus plus instead of plus or minus. Of course, it doesn't really matter. I could write plus or minus, but just to be a little less confusing as far as what I really did, with the plus 255.712, I really was subtracting, and with the minus 255.712, I was really adding. Now, because I'm squaring both sides as part of the solution, I squared both sides right here. It's possible that I get what are called extraneous solutions that don't solve the original equation. That's possible. We'll have to use technology to see if one of these is extraneous and not a solution we want. Everything look okay as far as my algebra that you can tell? So one mistake was found. Make sure you let me know if you think you find another mistake. So 830 minus 255.712, that one's 574.288. And 830 plus 255.712, that one is 1085.712. All right, let's see if one of those is extraneous. Let's plot the function. I'm going to plot the original function here, this cost function. So that's 2.7x plus 4.7 times, careful, square root of 350 squared plus, in parentheses, 830 minus x quantity squared. Looking right here. Hopefully I didn't make a mistake typing that in. I think it's okay. Let's see if it works here. Pick a window. Oh, say, well, you know, x can't actually, let's think about this a little bit more. X has to be the smaller one if it's going to work. Because based on this picture, x can't get bigger than 830. I'll go ahead and plot it out to, say, 1200 just to see what happens anyway. The y coordinate is a cost. What kind of ballpark should I expect for y values here? Well, you know, if x is in the ballpark of, say, 574, this would get multiplied by 2.7 approximately, and that is going to be in the ballpark of, say, 1500 or so. And this distance, say, is just pretend is around 400. That gets multiplied by 4.7. That would be in the ballpark of 2000 or so. Better go up to at least the sum of those two, 1600 plus 2000 or so. Let me just play it safe and go up to 4000. Let's see if we see a graph. We do. And it looks like there's a minimum. Let's go up higher to see it better. A minimum perhaps near 574. We can look for it. This is looking pretty good, isn't it? Well, I'm off by 10 units approximately. 584.36 is what the calculator is giving me, whereas I got 574.29. So I must have made a mistake somewhere. It's close enough. That I'm unsure where the mistake is. I think for the sake of time, I won't try finding it. Do you think you see? Are you talking about right here? I squared the 4.7. Is that what you're referring to? .7 squared is the 22.09. Evidently, there's a mistake somewhere. Let me just quick check the calculation again here. .7 squared is 22.09. 2.7 squared is the 7.29. 22.09 minus 7.29 is the 14.8. 350 squared times 7.29. And then multiply or divide by 14.8. No. And then take the square root. Okay, looks like my mistake is right there, actually. Looks like I should have gotten 245.64 there. And that makes 245.64 here. 830 minus that is the one we're after. All right, that looks better. 584.36. And in the graph, I believe that was the minimum, right? Yeah, 584.36. So that's the value of x that's going to minimize the cost. What's the actual minimum cost? It's somewhere on your screen. What's the actual minimum cost in dollars? Somewhere on the left side. Right there, the y coordinate, that's the minimum cost. About $3,587. Yeah, this other number, which was not quite right here, that I just scratched off, is an extraneous solution. When you solve equations algebraically and you end up squaring both sides of an equation, sometimes you get extraneous solutions. Solutions of the squared equation that don't solve the original equation. And yeah, I let my x go up high enough that I would have seen the other critical point here if it was there. Make sure here. Okay, yeah. That was an extraneous one. So that's something to watch for. Before class on Friday, you may need to find somebody who's got a protractor. What I want you to do, and I'll put this in the message, is I want you to try to model this as a trapezoid instead of a rectangle. So you can get a piece of paper, and if you made a printout, you should make a printout. You can trace this approximately. Doesn't have to be perfect. I'm not looking for perfection here. And my quick sketch here is definitely far from perfection. Something in that ballpark where you now connect these lines here because that's the top of the wetlands. I just did it really quick. If I went slower, I'd be more careful. I probably will redo this and try to go slower. So draw the trapezoid, and I want you to measure, find somebody with a protractor and measure this angle right here. It's going to be bigger than 180 degrees. And because different people will have different drawings, probably no two people will get the exact same angle, or at least if you were rounding to the nearest tenth of a degree or something like that, which I wouldn't expect. The nearest degree is fine. And then I'm going to maybe ask you a few other questions about it. What we're ultimately after is going from B up this way and then going this way before crossing the wetlands to get up to A. That's what we're ultimately after. And I may have also ask you to write down a cost formula if this is your unknown variable distance. There's a triangle that you can draw in here. It's no longer a right triangle. And because of that, you're going to need the law of cosines, which probably most people have forgotten. You'll need the law of cosines if you're going to ultimately figure out how the total cost of going along here and then along here depends on X. These two parts are in dry land. This part is the wetlands. Okay, I'll probably give you some more hints in my message.